In this question, we're told that Bob's hobby is using his metal detector to look for objects in the ground. The local farmer, Diane, lets him look in a large field that she owns. When the metal detector signals a find to Bob, he digs it up and he classifies it as either interesting or rubbish. Only 10% of the finds are classified as interesting. Bob looks for objects in a large field every day for 5 consecutive days. He decides that he will keep looking each day until he's found one interesting object and then he will stop. So, the first part of the question asks us to state an assumption Bob might make to model the number of objects he digs up in a day with a geometric distribution. So I was getting the feel of a geometric distribution. He was going to end at his first success, the first time he found something interesting. But they've told us that, so we don't get any marks for naming the distribution, but we need to talk about an assumption that's linked to that distribution. Well, the assumptions that Bob can make, firstly, is that the items, the interesting items, are spread evenly around the field, so that the probability that he collects one interesting item is independent from the probability he finds or digs up a second interesting item, so they're not in clusters around the field. Apart from that, that means that the probability of finding an interesting item is constant. It's always the same probability. The interesting items aren't diminishing, they're not running out. The same probability, 0.1, of finding an interesting item. In part B, we're told to use this assumption to calculate the probability that he digs up 7 objects on the first day. So it's a geometric distribution. Let's just get that down. X follows a geometric of 0.1. Now the probability X equals 7. For him to have 7 attempts to dig, that means the first 6 attempts were failures and there was 1 success. So P times Q to the power of 6, 0.1 times 0.9 to the power of 6, and that is 0.0531. In part C, we now need to find the probability that he digs up more than 7 objects on the first day. More than 7 is equivalent to greater than or equal to 8. If he needs to dig more than 8 times, the only reason is because he's had at least 7 failures. 7 failures have definitely occurred. So Q to the power of 7, that's 0.9 to the power of 7, and that gets small quite quickly when you raise 9 to the power of 7. We get 0.4783. Okay, in part D, we're asked to find the probability he digs up fewer than 7 objects each day on 3 out of the 5 days. Now that we're referring to the 5 days, those 5 days are 5 trials. They're 5 attempts to go out digging. This is now the binomial distribution, and we're looking for 3 successes from those 5 days. But we need to find the probability of success for this binomial distribution. And the probability of success is defined here. The probability he digs up fewer than 7 objects. So let's find that probability first. Him digging fewer than 7 objects is the same as digging less than or equal to 6 objects. And now that means one thing we know didn't happen is he didn't have 6 failures. So I can do 1 minus failure to the power of 6. 1 minus Q to the power of 6. 1 minus 0.9 to the power of 6. And we get 0.4686. Now that's the p-value that we need to use in the binomial. So just stating the binomial here. Y follows a binomial. N equals 5. P equals 0.4686. The probability that Y equals 3. The probability of 3 successes. The probability that he digs up fewer than 7 objects on 3 out of the 5 days. That's going to come from the binomial probability function. 3 is the minimum, 3 is the maximum, 5, and the probability we just found. So that gives us an answer here of 0.2905. Just before E, we're told that over the summer, Bob looks for objects in this large field for a total of 80 days. So N equals 80. We're asked to estimate the probability that the mean number of objects which Bob digs up each day is fewer than 9. The mention of the mean there, we're looking for a probability of the mean. Here we know we're working with the X-bar distribution. So that's actually the central limit theorem. What we need operate the central limit theorem is a value for n, the expectation of this distribution, and the variance of this distribution. Well, the expectation of x, that's 1 over p. So 1 over 0.1, that's 10. Expectation of 10. The variance is q over p squared, 0.9 over 0.1 squared, and that gets us 90. So we have the expectation and the variance. We can put together the x bar distribution. Mu is going to be 10, and sigma over root n is equivalent to root 90 over 80. Let's make sure we put on the squared. And we're looking for the probability that x bar is less than 9. On a diagram, this is the region we're looking for. NCD, arbitrarily small value of negative 1000. We've got our 9 as the upper limit, and then our standard deviation and our value for mu. All into the calculator, and we get 0.1729. The probability that the mean number of objects Bob digs up each day is fewer than 9, 0.1729.